Okay, so just as a review, right, we looked at this problem here, right? Basically, what we can do is we can actually factor out the x minus 6, okay? And that's still going to be true. We factor out the x minus 6 here out of the limit, and we end up with the limit as x approaches 6 positive of x, and that's just 6, all right? But we have to actually think about the sign. We have to make sure that we think about the sign. Remember, I pointed to that yesterday. And so how we think about that sign is we say, okay, well, this is the reasoning right here. Anything greater than 6 will make x squared minus 6x positive, okay? And the absolute value is going to be positive. So we have a positive over a positive. That means our answer is going to be positive, okay? So now what do you think about, call this number 2 here there, Eric? You want to work through that with me?
Yeah.
Okay,
This is
cool.
it.
Okay, so
So same thing, you take out the x from the top. So you'll have x minus 6, and then you'll have the x on the outside.
uh-huh.
Bottom, you have x minus 6.
Mm-hmm.
And so in this case, you would do the same thing, cancel the x minus 6 and the x minus 6 on the top.
Kind of, yes. I mean, like, basically, the difference is, yeah, okay, we'll allow that to happen. But don't forget, all right, it's going to equal x. However, what? The difference
The
here.
x has to be coming from the left side.
It is. So what does
So
that mean about? Yeah,
it's negative.
yeah. So that's going to be negative. So this is actually going to end up equaling negative 6. Okay,
Mhm.
right? Because it's going to approach negative 6, right? And on the top, it's going to approach positive 6. So in fact, there's not just a hole, there's a jump there. We've got to jump
Yeah.
discontinuity, right? Okay, because of that absolute value. Awesome. Thanks so much, Eric.
Hmm.
Does that make sense?
Yeah, that makes sense.
Okay, cool. Yeah. I mean, like, if I don't give you the difference quotient, you don't have to use the difference quotient. That's a straight up limit problem.
Yeah, no, it's because I was this morning I was watching your videos and doing that. So as soon as I saw this, I guess I was already in that state of mind, just doing that.
Totally got
Yeah,
it. I know how that feels. I've been there.
yeah.
All right. Cool. Thanks, man. All right. So I have a question. Does this work every time? Well, here's the thing. Okay. Um, so, all right. This is technically, I got to be careful here. Okay. It's technically not the limit as x approaches 6 minus of x. It's not exactly true. Okay. And that's why I was kind of a little hesitant to say that that's actually going to equal that. It will equal 6, but it's going to be negative 6 because of the absolute value. Okay. No, it's negative, man. Right? Because if you look here, watch. If x, all right, so let's just confirm that this case. If x is less than 6, then x squared minus 6x is negative, right? And we're thinking about limits, right? A limit is just what happens as I get close to 6, not when I hit 6, but as I get close to 6. So as I get closer and closer and closer to 6 on the negative side, I'm in the negative area. They're all negative. All those values are negative. So I'm going to be approaching negative 6, not positive 6. All right? Okay? And that's because x squared minus 6x is negative. Absolute value of x minus 6 is positive. All right? So there's an argument actually that's needed to be made here. All right? This is not exactly true. All right? It is and it's not. Okay? Because the limit as x approaches 6 negative of x is 6. They're different and they're different limits. Okay? So maybe we actually want to just say, well, okay, this is going to equal negative 6, all right? And basically, because if then x squared minus 6x is negative and absolute value of x minus 6 is positive, okay? So x squared minus 6x over the absolute value of x minus 6 is negative for all x less than 6. And that's why our limit is actually equal to a negative number. Hold on, I got a bunch of people went to the chat. Okay, sorry. Okay. So, does this work every time? Well, you've got to reason through it. You've got to be thinking about what does it mean to be a limit there, Ismar. All right. the idea of a limit is that as I get close from one side, or a one-sided limit, excuse me, as I get close from one side, what's happening to those values? Okay. And as I get close to the other side, what's happening to those values? All right. So sometimes something looks like this, like with an absolute value, right? Other times, it's not one size fits all. All right. So you've got to be kind of like, we want to work on understanding what the limit is. I don't know if that answers that question.
Right. I was just wondering for
Mhm.
the absolute value. Like,
Yeah,
not
I mean,
not for all limits, but for this particular type.
excellent. Okay. So that's a great question. I mean, you know what? I would test. If I get an absolute value somewhere, I'm going to test out some points just to see what the sign is. Because my thinking on it always is if I have an absolute value, it's going to do something funky to my signs. All right. So I would say that you should check it. Like you should, it should make you pause. That's what it should make you do. You should pause, you check it out. You're like, okay, what's happening to the signs here if I've got an absolute value on there? Does that make sense?
Yeah, thank you.
You're welcome. Misha, I didn't just answer, add a negative onto the end of my answer, right? I actually had to reason through to make sure that it was going to be negative, right? And so is that what you were asking? Maybe you can unmute and tell me.
I was kind of referring back to where you put x times x minus 6 over the absolute value of x minus 6.
Mm-hmm.
Couldn't you have put a negative in front of x minus 6 and solved it like that? Or is that
Good
not?
question. It's true. It's totally true. That
Okay.
Yes, you could, but you would still have had to make this argument down here. This argument, the x less than 6, so we end up with a negative. So I'm going to turn this other one into a negative. Does that make
Okay.
sense?
Yeah.
It's not like you had, because you don't have two answers. You have different right-handed and left-handed limits.
Yeah.
Does that make that follow?
Yeah. I think I got that. Yeah.
Okay. So you'd still have to make a little bit of an argument down here, a little bit of like an explanation. All right. Just, like, okay, well, as I get close here, I'm going to be in the negative direction. As I get close over here, I'm going to be positive. So they're not actually going to be equal to each other.
Hey, Professor. So on the test,
Sure.
at the very bottom, so like after you get -6 and you test it and do the proof, is that part of the answer?
Yeah. I mean, like you basically tell me, like you'd reason as to why you got -6. You'd say, well, I figured out that coming from the left-hand side, all my values are going to be negative, right?
Okay.
X squared minus 6x is going to be negative over positive, that kind of thing. So yes, you would put something in like that.
Okay.
Yeah. It's a little weird because it's like, when do I write a couple sentences to answer a math question? For limits, you do sometimes. Okay. And then John, you said, wasn't it positive? And like I said, no, it's actually going to end up being negative. Does that answer your question? You can unmute if you need to.
Yes, it does. All
right, awesome. Cool. Great. So that's good. Now, I had a question. There were a couple questions on the discussion board. I'm going to do one of them. The other ones I put answers to on the discussion board. Sabrina, to your question, I'm going to make a video of that particular one and post it. I think that would be a better way to do that. That particular question, right? That is true. Exactly. So that's a perfect explanation. Okay. I just think because it's not like I'm not too worried about that kind of question as we like work towards the exam, that kind of thing. All righty. So let's go in here. Open this. You'll see, hey, look, all that homework. Now, what we want to look at now, the question that I had was from 2.3, number 52. Okay, and this is g of x, right? We've got this piecewise function, g of x equals, okay, x if x is less than 1, 3 if x equals 1, 2 minus x squared if x is greater than 1 and less than or equal to 2. And then x minus 3 if x is greater than 2. Okay. And so we're asked to find some limits here. I just wish, all right, the limit as x approaches 1 from the negative side. So the limit, first, as x approaches 1 from the negative side, okay, of f of g of x. And if we look at that, all right, so we're going to be, this is the one we're going to look at because this is what happens. That's x less than 1, okay? So there's x less than 1. And so what we want to see is that we're just going to get x as x approaches, right, from the negative side, okay, as we approach from the negative end. So this is going to end up just being 1. That's what's going to happen, right? Because we've got that as x is less than 1. Two, actually, these are Roman numeral 1, Roman numeral 2. Okay. The limit as x approaches 1 of g of x. Well, now that's more complicated, okay? And so that's more complicated because, let's think through, right? We need the limit as x approaches 1 from the negative g of x to equal the limit as x approaches 1 from the positive of g of x. Okay? Now, we got to check. Which one is actually going to be, we know the one from the negative side, that's going to be 1. We need the one from the positive side. Which one of these three? Let's call this number 1, number 2, number 3, number 4. Which one of those 1 through 4 is actually going to tell me the limit as x approaches 1 the limit is that x approaches 1 from the positive side?
Third one?
Yep. Okay. Yeah, so this one right here, that's going to be it, right? Okay, it's number 3. It's number 3 because we've got x greater than 1. Okay, we got x greater than 1. So, right, we're looking at the limit as x approaches 1 from the positive end of 2 minus x squared. Okay, that's a polynomial. We could just plug things in there. So this ends up giving me 2 minus 1 squared, which equals 1. Ooh, that's good. Good news, right? So the limit as x approaches 1 of g of x is equal to 1. All right, we've got those two. They actually match, so that equals 1. All right, and we have to do that because this is a piecewise function. Let me actually. In normal functions, right, we just have to, well, we'll still have to do positive side left, negative side, yeah. Okay. Right, number 3, we want g of 1. Say we got g of 1. What's g of 1 going to be? There we are.
3.
Yeah, you're going to use number 2, but the answer is 3. So yeah, it's going to be 3. Okay, and that's because this, if x equals 1, this equals 3. Okay, yep. So here's a question. What does that mean about the graph? What does that mean about the function, right? In terms of some of the things that we've learned. You can put your answer into the text box. The limit here, the limit as x approaches 1 of g of x equals 1, but g of 1 equals 3. Some of the things that we've been working with. This is the kind of thing we want to think through in terms of our. There is a point at 1, 3. That's very true. But let's think the calculus. Yeah. So there we go. Yeah, there's a hole, and that means, yep, that's Ricardo's got it, Phoebe's got it, okay? There's a hole, and that hole means that the function's not continuous, all right? So basically what we have here is we have a discontinuous function. Now I know that that's not 2.3, okay, but it's something to actually look out for and something to kind of think about, okay? So we'll put a little side note. Since the limit as x approaches 1 of g of x, right, does not equal g of 1, this function's not continuous. Okay? So that's actually how we say, okay, that's not a continuous function. All right? Let's look at 4. All right, the limit as x approaches 2 negative. All right, let's see what we've got here. The limit as x approaches 2 negative. So which one of these parts of the function, 1, 2, 3, or 4, is going to be used for the limit as x approaches 2 negative? There it is. Yep. Yeah, so it's going to be number 3, okay? And so what we're looking for is 2 minus x squared. Or, excuse me, g of x is going to equal the limit as x approaches 2 negative of 2 minus x squared, which equals 2 minus 2 squared, which equals negative 2. Okay? And we have 5. What about the limit as x approaches 2 positive of g of x? We're going to use number 4. That's right. And then what is it going to be? So you're going to use number 4. And so what's the value for the limit going to be for 2 positive? What's this limit going to be? So we'll use number 4. There it is. Yep, it's going to equal, right, negative 1, because we can just do this by substitution. Okay, so it's negative 1. So what does that mean? So what about is this number 6? Yep. What about the limit as x approaches 2? What does that mean? Yep. Does not exist because the limit as x approaches 2 from the positive of g of x does not equal the limit as x approaches 2 from the negative of g of x. Great. Does not exist. Good. All right. Cool. And then it says to draw the graph. All right, we'll do it. Here we go. Draw along with me, right? We got some our problem points are at 1 and 2, right? Okay. 7. Okay. At 1, so I'm gonna kind of think about what's happening at 1. Let me see. Well, at x equals 1, g of x is equal to 3. So I'm doing 1, 2, 3. So there it is. There's that. Okay. But I know that the right-hand limit and the left-hand limit are both going to end up at 1. So I've got a hole right there at 1. Right? Remember, those were like our first 2 questions. The limit as x approaches 1 negative was 1. The limit as x approaches 1 positive was also 1. So they're both going to be at 1. So I know that I've got a hole right there. Okay. And then I also know that the limit as x approaches 2 from the positive end is going to be negative 1. Okay. So this is going to be down here at negative 1, but it's not going to be included there. And the reason why, okay, is because, oh, actually it is going to be included. Sorry. So that is included. Right. And that's because of right here. That's the less than or equal to. So it's got to be included because it's going to be equal to at that point as well. Wait, no, that's wrong. It's -2 is the one that's down here. The -2 one is the one, and it's the -1 one that is not included. Okay. This guy is 2 minus x squared. So it kind of looks like that. Doesn't touch that circular point, but kind of moves through that. It's an upside down parabola. Okay. We've got a y equals x. There's that. That's that line right there. Okay. And then we've got x minus 3. So that is just a straight line there. Here is x minus 3. Here is x, y equals x. Here is y equals 2 minus x squared. Woofles. Really, a lot of great review stuff on that, though. Really nice problem for review, from a review perspective. Not so much the graph. I mean, well, actually the graph is good because if you follow along with what's going on in the graph, you can see, you know, what it looks like to have discontinuities. We've got a bunch of discontinuities there. Wait. That's not what that looks like. Remember, it does actually, it goes right here, doesn't it? The limit as x approaches 1 is actually equal to -1. It's just that we have this jump discontinuity up at the top. Nope. Right, we have g of x equals, it's hard sometimes because I can't see the other part of the thing. It's going to be g of x was x if x is less than 1, 1, or not 1, but 3 if x equals 1, 2 minus x squared if we've got 1 less than x less than or equal to 2, and we had x minus 3 if x is greater than 2. Great. There you go. So that's our graph. All right. Cool. Does that help you out, Christian? Hope so.
Yeah.
Okay, cool. All right. Bunch of great stuff here. Let's just go over this and then we'll take a break. All right. One, right? We've got a piecewise function. So we've got a piecewise function. And what we want to see, right? It's just, this one's kind of helping us to think about what a right-handed limit is and a left-handed limit is, right? But what we've got here too is that once a limit exists, right, or is equal to a number L, if it's right-handed limit and its left-handed limit agree, right? We know that. That's actually a really important theorem. It's a definition theorem. So we just showed that like with 1 and 2 right here, okay? But if we have a hole in the graph like we do here, okay, then we could very possibly have it be not continuous, right? Since, and we've got it right here, the limit as x approaches 1 of g of x doesn't equal g of 1, right? That's how we know it's not continuous. It doesn't like match that requirement, all right? Okay. Now, if I wanted to actually make this graph continuous, what could I do? If I wanted to make it continuous at 1, excuse me. If I wanted to make the graph continuous at 1, that's weird. Sorry. What could I do? I wanted to make the function continuous at 1. Any ideas? There we got somebody in the chat. Okay, we don't want to remove g of x equals, well, yes, we want to remove g of x equals 3, but what do we need to replace it with something. Yeah, we want to make g of 1 equal to 1. Okay, right? We make g of 1 equal to 1. And by doing that, boom, now we're continuous, right? Because the limit, right, this thing would now not be true. Okay, it would now be equal to g of 1. And then we'd have a continuous. All right, so that's a great example. So that's one way, like a whole, a removable discontinuity can actually be made whole by putting in a value for g of x that actually fills in the hole. Now, what about here, right? We look over here, now we've got these two limits, right, are not equal to each other, so the limit does not exist. Can I make the function, this function, continuous at 2? Why or why not? We want to ask ourselves, okay, can we make it continuous at 2? Why or why not? Yeah, we can't. We cannot because this is a jump discontinuity. We cannot because this discontinuity is a jump discontinuity. This is a jump discontinuity. Yeah. So that's it. I mean, we'd have to fundamentally change the function completely, Valet. So we can't do that with this one. All right, great. That was a really nice question. Okay, so now let's take a look. What we want to do now is, so that was good. That gave us some opportunity to review some things for the exam. Let me, I'm going to go into Canvas in case you guys missed it. All right. So here's Canvas. Here's our Confer Zoom. Here's the announcements, okay? So here's the exam 1 announcement, all right? This is, I hope, as much information as you need. What you will see is in here, there's a bunch of information. I want you to read it. One of the values of reading too is that we tend to read more carefully than we listen. It's always a good thing. Reading, you learn more. You'll see here are, just like I promised, these are what the questions are going to be. Okay, they're not the exact questions. They are the topics on which the questions are going to be. There's 11 questions on the exam. Go take a look at them. Chapter 2, these are answers to the selected problems. That's a PDF for those of you who don't have OneNote. I'm going to get other people into OneNote in just a moment. But you can see those are going 2.1 through 2.6. I'll get 2.7 and 2.8 up later on, either today or early tomorrow. Okay, and then this is a past exam from a colleague of mine. You just need to look at the chapter 2 material in there. Okay. Well, Floor, I would be even stronger than that. The 11 questions that are in that exam 1 questions, those are exactly what the topics are for those questions. So like, you just need to be able, if I give you, here, let's take a look at it. Okay. How about this? Let's take that break. Let's take 10 minutes, be back at 11:50. Put your questions into the Zoom. I will answer all of them when we get back from the test. Misha, look at the exam 1 questions. You'll see how many. There are 11. Okay, so go ahead, read this on the break. Okay, read over the stuff, and then ask your questions when we get back from the break. Everybody got it? Okay. We'll be back at 11:50. I'll answer everything, I promise. All right. So you guys got to take a look at that. Okay. So go through here. Here are the questions that I got here. So those are the questions we should focus on, right? This is floor. And the answer is yes. In fact, like I said, basically if you go in, right, stop my share for just a second. If I go in here, here's the set, right? There are, oh wait, I'm not sharing yet. Go. All right, when we look at this, there will be 11 questions on the exam. The first question will be about using a table to estimate a limit, and then so on and so forth. Okay, and so basically, now there are a lot of leeway. There's a lot of leeway inside of each one of these questions. You have to kind of have a broad understanding of how to do any one of these questions. Okay, except for this proving a limit using the precise definition of a limit. All right, that's like section 2.4. I said you can use a template for that one. That one, pretty darn straightforward. It's going to be really straightforward, right? Basically, if you could do that, you're good. Okay, and that's also why it's only worth 5 points. But the rest of them, you want to make sure that obviously you need to make sure that you've done all the homework. The videos that I posted and the notes that we've done in class should also help you with the kinds of things that you should be thinking about. And the more fully that you understand, say, for example, how to find a limit using limit laws in algebra, the better that you're going to do on, say, numbers 3 and 4. Okay? So the answer is yes. These are the things that you should be focusing on. Completely. No. Okay. All right. So now I'll get to that in just a second. There is more. Misha, there are 11 questions on the test. Did I answer that question? How in depth should our answers and explanations be? That's Gabriella. And so Gabriella, you just want to be able to show, you need to answer the questions in the way that we've been answering them in class and inside of the homework. Okay. And so if you take a look, right, inside of there, I've got answers to selected problems. There are methods that I've been using inside of the videos. So you want to make sure that you go in, you understand what those methods are. Okay. You can of course ask me too, right? You can ask me during during the exam if you have any other questions about it. Right? You can message me privately. So I'm thinking that most of them will be two. I'm thinking that probably. Oh gosh, what was I thinking? I'm sorry, lost my train of thought. Probably between 1 and 2 sentences for most explanations. Like for example, if we think about proving a function is continuous or not continuous at a point, to prove it's continuous, you've got 3 things that you've got to show, right? And they're enumerated in the book, they're enumerated in the video, we've enumerated them in class, and they're also on the homework portions. So you can go in, take a look at, okay, that's how I prove that something's continuous or not continuous at a point, right? So there shouldn't be any too huge mysteries here. In fact, I want to take all the mystery out of it. I just want you to learn calculus. Does that help, Gabriella? All right, awesome. And then what people have been saying inside of the thing, yes, number 6 is proving the limit using the precise definition of the limit. That's epsilon delta. Number 6, and Rashi, no, it's based upon completion. There we go. Okay, if you do have questions over the weekend, whatever, feel free to email me. I will respond. Okay. Oh no. Okay. So Christian asked, would we just write it's continuous by writing it's a polynomial or something? All right. So no, right? I will say something like prove a function is continuous at this point right? Using the definition of continuity. And in that case, you know, you have to show the three aspects of being continuous. If I ask you, on the other hand, prove a function is continuous on an interval, you can say something like it's a polynomial, it's a rational function, right? Okay, right? This is the interval that it's actually continuous on, right? Because we have those theorems. That's fine. So for number 7, what I'm looking for is utilizing that definition of continuity. For number 8, it's more like utilizing the continuity kind of laws or those continuity principles and all those things that you know to be continuous, right? Trigonometric functions, rational functions, polynomials, things like that. Does that make sense? All right. Okay. So shall we, let's finish up 2.6. Oh, first things first. Okay. I need to make a correction. Okay, here's the correction. We go to chapter 2. This is inside of the precise definition of the limit. Okay. And on these problems right here, the ones where we were given an epsilon and we need to find a delta, it is not the max. Okay, so we go through, we find each one of the deltas. Okay, it should be the minimum of the deltas. Okay, not the max. Okay. Okay. Hold on one second, John. All right, so make note of that. I'm going to dump that video that I have where I say it's the max. It's actually the min. Okay, that was pointed out to me. Thank you, Christian. Right, it should be the min and not the max. Okay, everybody got that? So that's a change. Okay. Yeah, we could, Misha. All right. So yeah, there it is. Okay. That's the first thing. So we need to change that now. Let's go now to, let's do some limits at infinity. And okay, so we're working on horizontal asymptotes and limits at infinity. And we did this one. And then my brain froze for a little bit. Okay. All right. So we had here the find the limit or show that it does not exist. Okay. This is way easier than I made it out to be. So basically, if you look at this, the limit as x approaches infinity, I'm going to kind of do a little bit of work here, is going to end up equaling. So this thing here equals the limit as x approaches infinity of x plus the limit as x approaches infinity, right? Okay, of the square root of x squared plus 2x, okay? Which ends up equaling the limit as x approaches infinity of x plus the limit, or plus the square root of this limit as x approaches infinity of x squared plus 2x. So those are just some limit laws, all right? And the only reason why I'm doing this is really to like demonstrate. For something like this, for example, you could just write, this is like infinity plus infinity. So it's infinity, all right? It's gonna end up being infinity, all right? That's perfectly allowable. That's valid. I can see what's going on there. If I look here, I've got, this is gonna equal this one here, that first piece, that's gonna be infinity, okay? And then this second piece, what's under the radical is infinity. So it's gonna be plus, like the square root of infinity. Well, that's still infinity. That's infinity plus infinity, right? Keeps getting bigger all the time. And so add two infinities together, get infinity again, okay? Like the whole idea here is just understand, okay? Understand that the value of x keeps getting bigger, and we are just adding more to it. So basically all we're doing with this one is we just ended up adding infinities, which is just going to end up being infinity, okay? Same if you multiply two infinities together. That's still just infinity. It's might as well. It's getting really, really large. There's no problem there, okay? All right, which actually should give us a note here. Put this in here. This is a note. Here's our note. And the note is this. Infinity plus infinity, that's just infinity. That's, you know, stuff just keeps getting bigger. Infinity times infinity, still infinity. Okay? 0 times infinity, that's undefined. We've got to do something with that. If they're both positive, Carla. Yeah, so Carla asked, when adding and multiplying infinity, we will always get positive infinity. Well, the question is if they're both positive. Okay, for our purposes, yes, for right now. We'll see some different places where it's a little tricky, okay? Infinity minus infinity. That's also undefined. We don't know what that means. Infinity divided by infinity, also undefined. So we've got to do something with that. Okay? Infinity divided by 0, also undefined. We're going to see these guys a lot more, right? We're going to see these a lot more when we do something called L'Hopital's. Danny was talking about that earlier. But just for our purposes right now, if you add two infinities together, you're going to get infinity, okay? All right. I'll address that in a minute, Stephanie. Yep. Positive infinity times a negative infinity, also undefined. So you have a positive infinity times a negative infinity is also going to end up being undefined. That's problematic. Okay. And yeah, radical infinity, just infinity. Okay. If you think about it, like this one here, like, is this 0? Is one of the infinities bigger than the other infinity? This one here, like, is that 1? I don't know, right? It's infinity. I don't know what that means. This one's really weird. But like these guys here, I'm just taking a really big number and adding another really big number to it. So that's going to be infinity. And this one here, same thing. Same thing with the radical. So I'm taking the square root of a really large number. It's still just getting bigger. I mean, it's still just getting larger and larger and larger, and so consequently, you know, it's just going to be infinity. Okay. It's a good question, Sabrina. It depends. So you can use the limit laws for like this guy. Well, you can use the limit laws anytime you want to. So Sabrina asked, can we use the limit laws to find a limit instead of simplifying, or do we only use the limit laws when we're asked to? Well, you can use the limit laws anytime you want to. Okay. In fact, sometimes it's going to be a really good idea to use them depending upon the circumstances. It's like one of the tools that you get in your toolbox. Okay, to like work on these for. But sometimes it's not going to help, right? And we'll see a couple of examples where we're going to have to do something somewhat different algebraically in order for us to get this actual limit. Okay, so the answer there again is it depends. It depends upon the circumstance. And then Danny asked, is infinity considered a constant? No, it's not, Danny. It is not.
It actually is a concept. Oh.
Infinity is a concept. It's not a constant, right? It's like a way of thinking. A constant is a value that stays the same no matter what, okay? And infinity is not one of those. All right, so now I had a couple other questions. All right. So John asked, to get points for the questions on the test, do we only get points if we get the entire question correct, or is there partial credit? So this is just, let's not get on a test tangent, but I want to make sure to answer this one. There is partial credit allowed. Okay, there is partial credit, and I will provide you with a rubric after I've graded the test, so you see what the partials are for. Okay, and then Stephanie asked, how did you say we could access the notes later? It's on OneNote, and there is an announcement in which I describe how to get into OneNote inside of Canvas. All right. All right. Will we be on Zoom as well as Cam? Okay. All right. So got it, Mina. That actually is, it's a good question. You will only be on Zoom. You are not going to be on Proctorio. So like you're going to enter Zoom via Canvas. Okay. But there's not going to be an issue with you leaving Canvas as long as you're still in Zoom. Does that answer the question? It's not like we're using Proctorio. Okay. All right, cool. So let's back to math. All right. Okay, so cool. Let's take a look then. We're going to go a little bit further down. We're now on page 6. Let's say we want to find the limit or show that it does not exist for the limit as x approaches 0 positive of tan inverse natural log of x. So basically what we need to do here, okay, is this is a composition of functions, okay? So I'm going to think about this as the limit as x approaches 0 for the positive of tan inverse, and then the limit, whatever. I'm going to think of it as tan inverse, okay? The limit as, so I'm going to need limit as x approaches b. Sorry. Stop! It's a stylus issue right now. Okay, how to write this to make it as simple as possible. Let's call this like a limit as x approaches, say, a b of tan inverse, okay, of the limit as x approaches 0 from the positive side of the natural log of x, okay? So it's a composition of functions. So what we have is we have a limit inside of a limit. So what we want to do first is we want to think, what's the limit as x approaches 0 positive of the natural log of x? Okay? Really, really important, guys, that you know this one. Put your answer into the text if you got it. Think about what happens to the natural log of x as we get close to 0 from the positive side, right? Natural log of x not defined at x, okay? What's happening to it as we get closer from the positive side? Shall we look at a graph? I think we shall. Okay.
Hey, Professor, why
Yeah.
did you put for the limit of tan while x approaches b?
Yeah.
Why did you put that?
I'm going to explain that in just a second. How about that? Like,
okay.
Yeah, I mean, like, that's for a teaching reason. I'll show you in just a second, okay?
Got it.
Just hold with me. Yeah. Okay. Yeah. So I'm in Desmos. Stop my share for just a second. Desmos. Okay. All right. So I want to get, here's the natural log of x. There's the natural log of x, guys. And if we look, yep, that's it. Let's take a look. It's got an asymptote at 0, right? It's got an asymptote at 0. And then as we get closer and closer to 0, went off the chart. Okay. As we get closer and closer to 0, it just keeps tunneling downward, right? It just goes towards negative infinity. So the limit as x approaches, x approaches 0 from the positive side of natural log of x is negative infinity. is negative infinity. Okay? So now what I'm thinking about, that's going to be like my b. So we're going to cut a sub. So now what we're really looking for is the limit as x approaches negative infinity of tangent, okay, of, say, whatever it is. It doesn't even matter what it is. What is g of x, okay, or x? Limit of tangent, call it x, okay? That's the second part. So our b becomes a negative infinity because that's what the natural log of x is as x approaches 0 from the positive side. So this part, this is negative infinity, right? So we know this is approaching negative infinity. What happens to tan inverse? What is this guy going to be? Think again. Think about it. It's tan inverse, right? What does tan inverse approach as we go towards negative infinity? Nope. Let me do the graph again. Okay. I need to start to use this one. There it is. Negative pi over 2. Negative pi over 2, guys. So now it's a horizontal asymptote. Okay? Right? So we started out here, we were in the natural log of x, we were approaching 0 from the positive side. That was negative infinity. And then we needed to figure out what the limit was as we approached negative infinity. And that limit ended up being negative pi over 2. Right? You have a horizontal asymptote at negative pi over 2 for tan inverse. And it has a positive pi over 2 for the limit as x approaches infinity for tan inverse. Yeah, trig. Made you guys take that, right? Okay. All right, so this thing here ends up equaling negative pi over 2. All right. Now, important. Let's make some, just so that you remember some of them, right? This one here, really important. Those inverse tangent ones, they're kind of necessary, right? Okay. Important, right? Horizontal asymptotes for important functions. Okay. Like, for example, trig functions. Well, inverse trig functions, we should say, inverse trig functions have horizontal asymptotes. Trig functions have vertical ones, right? Because they're inverses of each other. Study. Let's just throw that out there. The vertical asymptotes for trig functions, right? Okay. And the horizontal ones for their inverses. Okay. All right. Let's take a look. Okay. Then now find the horizontal and vertical asymptotes of y equals x squared plus 1 over 2x squared minus 3x minus 2. Okay. So let's first start out here. Let's have you guys find the vertical asymptotes. Find the vertical asymptotes. All right. You may have noticed. Exam question. Plus draw a graph. But yeah, something like this. Maybe not this kind of function. Could be a different function. But yeah, basically, that's the idea. That's right, Christian. Yeah. So we found the limit as we approach 0 from the positive side of natural log of x, right? And then that b was now going to be what we end up being the limit of to get tan inverse of x. Okay, gotcha. All right. So we look here, okay. Question, hey, Valet, tell me, how do I, or actually, Rashi, how do I find my vertical asymptotes?
I think you set the denominator equal to 0.
That's right. Set the denominator to equal to 0. I'm going to scroll all the way up now. There we go. Give myself some space. Yep. And so tell me what you did.
So first I I'm not sure what the exact name for it is, but I try to get it into like a form where it was like the 2 parentheses. So I did like 2x squared. Yeah, sorry, factoring, yes.
Yep.
And then so I got x minus 3 times x plus 1.
Minus 3 times x plus 1. Got it. Okay.
And then I set each of those equal to 0.
Great.
And then I got 3 and negative 1.
Totally. Exactly like you did in algebra, right? X plus 1 equals 0. Excellent. Thanks, Rashi. All right. Oh, so sorry. Wait. Keep there. So x equals 3 and 1. So our vertical asymptotes are where? What are our vertical asymptotes, Rashi?
Is it 3 and negative 1, or is
3
it
and negative 1? 3 and negative 1. You're absolutely right. Go too fast. Yeah, there's a problem with your fact. I agree. There should be a 2 in here. This should be 2x plus 1, isn't it?
Oh, sorry.
Yeah, it should be 2x plus 1. Right?
Professor, I got 2x plus 1 and x minus 2.
All right. Got it. Okay. Rashi, your idea was absolutely correct, but the execution was just a little off, right?
Okay, sorry.
All right. No worries. That's good. We get at it. Yeah. So we got 2x, right? Okay. Let me do this. I'll do it myself. And then we're going to have 2x minus 2. This would be plus 1, and then this is x minus 2. I got that. That's what I got, and that'll equal 0 then. All right? So then 2x plus 1 equals 0. So x equals negative 1/2. And then we'll have x minus 2 equals 0. So x equals 2. Great. Good. Okay? So our vertical asymptotes are got to be very careful here. They are x equals negative 1/2 and x equals 2. Vertical asymptotes are actual lines, everybody. So they have forms of lines, all right? And in fact, that's the proper way to write them, not just the number. You write negative 1/2 and you write just 2, I am going to take off points. That will be something that I'm looking for. Okay? Okay. Now, next up, horizontal asymptotes. Let's find the horizontal ones. What then? How How do we do that? Okay. Oh no, you could just write you could just do that. That's fine. But you have to like give me x equals 1/2 and x equals 2. Yeah. No, you don't have to write so our vertical asymptotes are. No, that's for the purposes of your notes. Okay. All right. How do I find my vertical asymptotes? Well, how'd you get that, Floor? All right. Hey, Bill, you want to give me a hand finding this horizontal asymptote?
You just x squared divided by 2x squared, and then you just cancel out the x squared.
Nope.
No.
Okay, got it. I understand. That's what you guys did inside of your pre-calculus class, and that's not wrong. Okay, that's not wrong. But we've got a process now. We actually need to. Our horizontal asymptotes are defined a little bit differently now. Okay, but thank you. I appreciate that. Anybody know how they get defined in calculus?
Don't you have to look at the two highest powers on the numerator and the denominator, and then if they're the same, you just divide the coefficients?
Okay, that's what Bill just said, and that's not wrong. It's just not what we've been doing inside of this chapter. All right.
Multiply both by top and bottom by 1/x².
Okay, but first we have to find the limit as x approaches infinity.
Right.
Yeah. Okay. So get this: horizontal asymptotes are what happens to the function as we go towards infinity or negative infinity. Okay. So infinity or negative infinity. Here's the thing. In pre-calc, they didn't actually explain it. What we're doing is we're like, okay, so this is the reason why what you just did works. It's not wrong, okay? It just lacks the explanation that we're going to need, okay? This is the explanation, all right? So the limit as x approaches infinity of x squared plus 1 over 2x squared minus 3x plus 2. Okay, great. So Valet, tell me what's going on. Tell me, what do I do next now?
You multiply top and bottom by 1/x².
Yeah, so what we're going to do is we're going to look at the highest power in the denominator, okay? And we're going to multiply the top and bottom by that, 1 over that highest power. This is then going to give me, right? So go ahead and simplify that. It's going to be 1 plus 1 over x squared divided by 2 minus 3 over x plus 2 over x squared, right? So again, if I ask you to find the horizontal asymptotes, this is what I'm asking you to do. So I'm glad that we came upon this little roadblock, okay? It's good. That way you guys are like, oh, now I get what he wants. This is what I'm looking for. A horizontal asymptote is what happens to the limit at infinity, okay? Now, what's going to happen is 1 over x squared, 3 over x, or negative 3 over x, and 2 over x squared are all going to 0, right? This one goes to 0, this one goes to 0, this one goes to 0, so we're just left with 1/2. So like I said, you're not wrong. Process isn't wrong, it's just not what we're doing now that we're working in calculus. Cool. So that's 1/2. So my asymptote is y equals 1/2. There we are.
Professor, why'd you put them all to 0?
Huh?
Why did you put them all to 0?
Why did I send them to 0? You have to. Basically, right, if they don't go to 0, then they're going to go to infinity. They're going to do one or the other. They're either going to go to 0, they're going to go to infinity. If one of them goes to infinity, right, okay, we've got to figure out if it's on the top or the bottom. If it's on the numerator and it goes to infinity, the whole thing's going to explode. It's going to go to infinity, okay? If it's in the denominator, then it's going to go down to 0. You follow me?
Yeah.
Right? But
Yeah.
that's why what we did, that's why we went in and we divided the top and the bottom by 1 over x squared. or multiply by the
Okay.
number. Yeah. All right. Does that answer your question? So here's my horizontal asymptote. All right. You should say, okay, you need to define, okay, just so that this is very clear, this is a horizontal asymptote, this is a vertical asymptote. So you should actually label them as vertical and horizontal asymptotes. Okay. So make sure that you do that if I ask you for both of them. Just say this one's a vertical, this one's a horizontal. All right. Okay. Any questions on that? We're going to do a couple more of these, and then hopefully we'll hop into some derivatives. Okay. Actually, okay, that's good. Yeah. Let's look at like a graph here, and what I mean by having a sketch. So let's say, for example, I have x. I know that x equals -1/2 and x equals 2 are my horizontal asymptote or vertical asymptotes. Vertical asymptotes. So label them like that, and then we'll have the horizontal asymptote. You know what? We should check. One more thing is going to be at y equals 1/2. What's that? Y equals 1/2. Okay. So my sketch right is going to have, here's like here's 1. Let's say this is 1. This is 2. Okay. Okay. So I have a vertical asymptote at -1/2. Okay. So it's got, here's my -1/2. And then I have another vertical asymptote at 2. Okay. And then I have a horizontal asymptote at 1/2. Okay. So now what I need to do is I know, okay, either I'm going to have, right, I'm going to have something that looks like this, right, because it's a vertical asymptote, or it's going to look like this, right? I'm going to have one or the other. Yes? I need to figure out which one it's going to be. I need to figure out which one it's going to be. Now we can do that using limits. Okay. Yeah, I'm going to do that. That's what I'm going to do for this for our purposes, Misha. Misha said just plug in a value. So I'm going to do exactly that because that's going to make my life a lot easier here. So let me get my function. It's x squared plus 1 over 2x squared minus 3x minus 2. X squared plus 1, 2x squared minus 3x minus 2. It's my f of x. Okay, so I'll choose a value over here. Like, let's say, for example, let's choose x equals 1, right? And I mean over in this region right here. So I'll pick x equals 1, okay? Or x equals -1, excuse me. -1, so this is now, right? This is going to equal 1 plus 1. So f of 1, where should I put this? F of 1 is going to equal 2 over, and then this is going to be 2 plus 3 is 5 minus 2, 2 over 3, okay? So 2 over 3 is above 1/2, right? Remember, this is y equals 1/2. So it's above y equals 1/2. So I'm just going to, it's going to go up in the upward direction, okay? That's what happens when you've got a vertical asymptote and a horizontal one, okay? Now, next question, we're now going to look over here, right? Let's look into this region. Let's do f of 0. Okay, f of 0 is just going to equal 1 over, and this will be -2. So it's going to be -1/2. So it's going to be down here. Okay, so it's probably going to look something like this. it's just a sketch. So we just want to kind of get like a look at what the sketch looks like. So there's the sketch. It probably looks something like that. Okay. And then finally we need one over here. So let's choose like 5. Well, we know that's going to be positive, but let's choose f of 5. Okay. And f of 5 is going to equal, right, 26. 26 divided by, and this will be like 50 minus whatever, 26 divided some positive number, right? Okay. And a positive number greater than 1/2. So let's check it actually. So this is gonna be 50 minus 15 minus 2. Okay. So that's actually, right, greater than 1/2. So it's gonna be up here. So you just test a couple points, throw them in there, and then that allows you to draw your sketch. All right. What I'm really looking for, make sure that those horizontal asymptotes are correct. I'm really looking for the vertical asymptote to be correct. Okay, that's the big part of what I'm really looking for. So once you find them, right, you can put them in the sketch, and then it kind of gives you a sense of what's happening inside of the picture. Okay. Give you a second to draw that. All right, let's take an 8-minute break. So let's go to 12:40. So we're gonna take a little bit of a break, and when we get back in, we'll finish this up, and we will go into we will begin working in derivatives. So I'll send you out an email. 2.8, we'll just have 2.8 be part of the next set of homework assignments. If you want to do it, you can definitely do it. I'm sure that you'll probably be able to with some videos and things of that nature. But if not, just focus on studying for the exam and then do some of 2.7 because there's a little piece of 2.7 on the exam. Okay. Not exactly. So Flora was like, the test is from 2.1 to 2.7. I'm going to give you the equation. I'll give you the equation for the tangent line, okay? And you're going to go find the equation of a tangent line. So like it's all from 2.1 really, but you're going to find a limit. You're going to find this limit for the slope. You'll find this limit for the slope, and then you'll go out and find the equation of the tangent line. So the thing is that if you know how to find the limit, doing this is pretty much what you've been doing throughout the entire chapter, okay? Plus the little part of finding the equation of the line. You don't have to have this memorized, though, for the next test, is kind of what I'm saying, right? I'll give you that equation on the exam. And that way you just like, okay, that's the equation for the slope. I'm going to need the slope, and here's the equation for the line. I find my equation for the line. Does that make sense? Okay, good. All right. And of course, if you do the 2.7 homework, then that question will actually be really easy, I think. I think it'll be simple if you do the 2.7 homework. If you don't, it's still very doable. That's what I mean. All right. So it's just like the introductory part of 2.7. Now, let's look. We now want to find the equation of the tangent line. All right, that's the thing that we're going to try and do. So the tangent line to the curve y equals f of x at the point P of A, f of A, is a line through P with the slope, and here's the slope of the tangent line. Now, if you watch the video, which you need to do, make sure that you do go in and watch the videos this week if you haven't done it, weekend if you haven't done it. Or you've been paying attention inside of the textbook, which all of you should have actually done some of the reading in the textbook. You'll know that this is actually what happens, okay, when we take the limit of the secant lines. Okay, this is the limit of the slopes of the secant lines. Secant lines. So that's actually the limit of the slope of the secant lines. All right? And so that's the equation for the slope of the tangent line. All right? So let's just kind of try that out. And by the way, this is, if you're like, again, furiously scribbling the definitions everywhere. It's in your book. It's in the videos, right? Yeah. And so let's, it's all over the place. And of course, inside of my notes. All right. So my slope, M, right? Let's say, for example, I'm going to do E1. So I'm going to do E1 here. Find the equation of the tangent line to the curve at the given point. Okay. So I've got y equals 4x minus x squared. Okay. And so my M is going to equal the limit as x approaches, and x is going to approach 2. X approaches 2. Okay. And that's going to be f of x. So f of x is your function, 4x minus 3x squared. Okay. And f of a, well, that's going to be negative 4. So it's minus negative 4 divided by x minus 2. Okay. And so like the real trick here is just to figure out what these things mean. All right. Or what the notation means. And you just got to do it step by step. This again, just like in the limits, that's an x value. A is an x value. Okay. So it's going to go in the denominator. There's your 2. F of A is a y value. Okay. And it's the one that goes with A. So it's going to be negative 4. Okay. And that's just functional notation. It'll be negative 4. And then f of x is just your function. It's this function right here. So this will then be, okay, let's kind of do some work here. This is going to be the limit as x approaches 2 of 4x minus 3x squared plus 4 over x minus 2. So now, again, we're kind of preparing for this exam. What are your thoughts, guys? Why don't we work through that? Find that limit. Right? What we want to do, we want to get x minus 2, okay, out of the denominator, right? We want to kind of cancel that somehow. That's our goal. Okay. Okay. Oftentimes it's just like, how fast can you do your algebra? Valet can do. Valet is very quick with his algebra. That's it. That it is. Yeah. So now, we got here, limit as x approaches 2, and we have x minus 2, right, times 3x plus 2 divided by, and this is negative, excuse me, negative, right, divided by x minus 2. That's my factor. I will cancel my x minus 2's out, okay, and I'll end up with then limit as x approaches 2 of negative 3x plus 2, and then I could just substitute. That's going to equal negative 3 times 2 plus 2, which equals negative 8. So just like any other one, any other limit that we're doing, what we're really trying to do is we're trying to do that cancellation. We're trying to get rid of the 0 in the denominator. Okay. Okay. Questions? That's it, right? Now, that's the slope. That's m. M equals the slope, okay? So I'm going to go down a little bit further, okay? M equals the slope. So now we actually need to find the equation of the tangent line, all right? That's the question it's asking for, the equation of the tangent line. So what I'm going to do is I'm going to use my point slope form, okay? Here's my point slope form. It's going to be y minus y1 equals m times x minus x1. This I will not be giving you on the exam, right? You need to have either the point slope form or, slope intercept form. You need to know how to find the equation of a line. But this means that we're going to get y minus a negative 4, right? We're going to put in our point. Y minus a negative 4 is going to equal negative 8 times x minus 2. And if we simplify, that's going to be y plus 4 equals negative 8x plus 16. And then that finally is going to be y equals negative 8x plus 12. And that is my final answer. This negative 8 here, the product of the product of this tangent line function is actually its slope. And then what we need to do is we need to plug in the slope into the equation of the line. Plus 16, and then I subtracted 4 from both sides. So yes, right? I've got y minus a negative 4, that's y plus 4, and then I have negative 8x plus 16. That's great, that's what I've got, and then I subtracted 4 from both sides. No worries. Maybe I should be more explicit. I'll do that next time. Oh, don't be sorry. Sometimes you never know. That's doing math. We're like, did they catch it or not? I'm not sure. Okay. Can I move on? Can I move up? All right. So yes, thank you. All right. So now we have this alternate definition of the slope of a tangent line. And here's the deal. The big thing that I want you to get, well, there's a bunch of big things that I want you to get out of this lesson. But one of the big things is that we've got a lot of ways of finding the slope of the tangent line, instantaneous velocity, and the derivative of a function at a point, but they're all basically the same thing, right? They really are all basically the same thing. So like we look at this here, and we say, okay, the tangent line of the curve, y equals f of x, the point P of A, f of A, is a line through P, Okay, so again, it's a line through P with a slope. And so this thing here, it's the slope. That's the slope of the tangent line. Okay, and we could just as easily use this equation as we could use the other equation. Okay, and I talk a lot more about that inside of the video. I talk about like why it is that the two of them actually are basically exactly the same. Okay, and all we're seeing right here, right, this is just kind of like, this is a graphic description of what's happening. I think the one that I have on the video is better. Okay, so don't, well, I like it better. How about that? Graphic description of this definition right here. Okay. So don't worry about figure 3. It's, like I said, it's in your notes. If you want to look at it, you can. Instead, this is really important. Okay. So the slope of the secant line is going to be your average rate of change. The slope of the tangent line is then going to be your instantaneous rate of change. Okay, so that's a big point here, right? Again, talked a lot about them inside of the videos to kind of like focus in on the idea that each one of these secant lines, they're an average, right? But then that tangent line, that's the limit, right? Remember this one here, it's the limit as x approaches a of f of x minus f of a all over x minus a, okay? So what you get here is you get like the difference between this whole idea of average and what happens when we add in the limit, okay? When I add in the limit, I get the instantaneous rates of change. The same thing's going to happen here for velocity, okay? Instantaneous velocity is the slope of the tangent line. It's an instantaneous rate of change, okay? So that's like our big difference here, okay? The big addition is the addition of this limiting activity. The limit as x approaches a of f of x minus f of a over x minus a, okay? All right. So it shouldn't come as too much of a surprise then that what we end up with is okay, this is the equation for the slope of the tangent line. In mathematics, okay, in math, if two concepts have the same exact equation, we say they are basically the same thing. All right, they have different concepts, right? Okay, like instantaneous velocity is like when I'm traveling through space, how fast am I traveling? Okay, and the slope of a tangent line, well, that's a slope, right? But they have the same exact equation, right? Same equation. So there's nothing, you need to make that connection. That's the connection that you need to make. That's a huge connection, okay? If somebody says, well, what's the instantaneous velocity? You're going to say to yourself, oh, it's the derivative, okay? What's the slope of the tangent line? Oh, it's the derivative, okay? Right? Because what we call the slope of the tangent line and what we call the instantaneous velocity, what we call this equation is the derivative. That's the derivative equation, okay? So instantaneous velocity, okay? The slope of the tangent line, instantaneous rate of change, they're all the same thing. They're all called the derivative, okay? And the only difference between what we're doing here in 2.7 and 2.8 is that this one is going to be derivatives at points, and 2.8 is derivatives along the entire function, okay? Got that? So if I say the slope of the tangent line, should be saying this to yourself, I mean the derivative. If I say the instantaneous rate of change, I mean the derivative. If I say the instantaneous velocity, I mean the derivative. Okay? Right? Cool. So, little foreshadowing here. Let's take a look at, like if a rock is thrown upward on Mars with a velocity of 10 meters per second, its height after t seconds is given by h equals 10t minus 1.86t squared. Find the velocity after 1 second, okay? So we want to know like v of 1, right? We want to know v of 1. Okay, that's what we're looking for here. Well, how do I find v of 1? I'm going to do this, okay? Yes? So what I'm going to say is I'm going to say, okay, well, I need to do that, right? I'm looking for a velocity. Here's my equation for velocity, right? As you progress, what you're going to do is you're going to say, I need to find the derivative of h. Okay, I'm going to find this, what I call dh dt. Okay?
What the shit?
Okay.
His message being like, are you okay?
Did you not answer calls? Like,
Sorry. All right. So that's what we're looking for, right? So we're going to have v of 1, right? And we're going to find the derivative of h. Okay? Then we're going to do that by taking the limit as h approaches 0, okay? And our f of x, all right, is h. Okay? F of x is equal to h, which equals 10t minus 1.86 t squared. Okay? So this is the limit as h approaches 0 of 10t minus 1.86 t squared. Okay? Our f of a is going to equal, well, okay, first I need to figure out what a is. Well, a is going to equal 1. Okay? That's because that's the value for the dependent variable. So after 1 second, so a equals 1. So f of a is going to be 10 times 1 minus 1.86 times 1 squared. Okay? And so that's going to equal, it's going to be minus, and that's going to be 8.14. Okay, 8.14. And we'll divide that through then by t minus 1. And then it gets divided through by t minus 1. So we did a little bit of work where we had to figure out, we had to make sure that we knew what f was.
and what?
So we have a equals 1, okay? And then f of a is going to be, we just plug in 1 into our function, okay? And now this guy here, okay, we're just going to go and find the limit, right? Go and find the limit. So go ahead and do that. Go and find the limit, right? That's the next part. So we've actually set it all up. Now I need you to just go and find this limit. I'll give you a hint, okay? Right? Factor out t minus 1. How about that? Factor out t minus 1. Let's kind of, so if I have t minus 1, I'm going to do a little bit of long division here. Negative 1.86 t squared, okay, minus plus 10t minus 8.14. This will end up being negative 1.86. Okay, so this is 86t. So that's negative 1.86 t squared. Okay, minus or plus 1.86 t. Okay, and so this is then going to be 8.14 t minus 8.14. All right, and so this is then going to be, oh, that looks like it's a minus 1, right? Or a plus 1, excuse me, plus 1. So that's going to then be, or not plus 1, 8.14, sorry. So this is 8.14 t, minus 8.14. That's a 0. Okay, good. So what that means then is that this limit, the limit as h approaches 0 of 10t minus 1.86 t squared minus 8.14, okay, divided by t minus 1 is going to equal the limit as h approaches 0 of t minus 1 times negative 1.86t plus 8.14 divided by t minus 1. That's then just going to be the limit as h approaches 0 of negative 1.86t plus 8.14. And then that is just 8.14. Yay. And that's his velocity after 1 second. 8.14, not 8.4. Yes, synthetic would also work. So Misha asked, "Does synthetic division would also work, correct?" And I said, yes, absolutely. I mean, one of the nice things that I just keep forgetting whether or not I should go positive or negative on which side when I do synthetic division. I just can't remember. And I don't want to compound my mistakes. How about that? But one thing to kind of get about this, if we're working, this is a polynomial, okay? So 10t minus 1.86 t squared minus 8.14, that's a polynomial, right? Okay, and so consequently, if we're kind of taking a derivative of polynomial, this actually should factor out. So we should be actually able to do like some kind of synthetic division or some kind of factoring or whatever in order to simplify this limit. All right, okay, to actually eliminate the t minus 1 from the bottom. Okay. What do you mean substitution, Ricardo? Do you want to unmute and tell me what you mean by that? He's asked, could we ever use substitution?
Where h before we did all the factoring, if we plugged in just a 0, wouldn't we get the same answer?
Cool. You are absolutely right. Stupid.
It's within the domain, right?
It absolutely is. I use the other equation. This is not the limit as h approaches 0. This should be the limit as t approaches 1. Okay. That makes this, by the way, equal to 10. Not equal to 10, but equal to, that just changes what this is. This should be t. I combine the two of them. Okay. I use the other definition of a limit rather than this definition. You are 100% Ricardo. You are 100% correct. But what we needed to get rid of the denominator because it was as t approaches 1. We'll do it the other way too. I'll just do it the other way in just a second. But this is the limit as t approaches 1, okay, of 10t minus 1.86 t squared minus 8.14. Then we have the t minus 1. Everything exactly the same. Okay. It just changes what this is. This is now equal to, this we can now substitute negative 1.86 times 1 plus 8.14. Okay. So that's 8.14 minus 1.86. Okay, and that's 6.28. Now, sorry. Let's use this definition for the instantaneous velocity in order to do this work too. Went too fast. Okay. All right. Now we have, okay, we're going to have V of A, right, is equal to, and this is going to be F of A plus H, right, minus F of A all over H. And we're going to take the limit of that as H approaches 0. Okay, so V of A is going to equal this. Okay, now we knew again that F of X was equal to our H, which equaled, let me get what that was again, 10t minus 1.86 t squared. So this is 10t minus 1.86 t squared. Okay, right? Great. Okay. And then minus F of A. Okay. In this case, F of A, it's going to be F of A is going to equal 10 times 1 minus 1.86 times 1, which equals 8.14. All right, so we still have that that's F of A. All right, and then let's, F of A plus H, okay, is going to equal F of 1 plus H, right, because A is 1. And so what we're going to need to do is we're going to need to have, this is going to be 10t minus 1.86 10t. This is going to be 10 times 1 plus h, okay, minus 1.86, 1 plus h squared. All right, because that we're going to need this term here, the F of A plus H. So what I'm going to do is I'm actually going to go and I'm going to simplify that. So this is going to end up giving me 10 plus h, 10 plus 10h, okay, minus, and then it's going to be 1.86 times, and this will be 1 plus 2h plus h squared. And that ends up equaling, okay, 10 plus 10h minus 1.86 minus, and this will be 3.72 h minus 1.86 h squared. So now I'm going to just plug all of that into here. So this is 10 plus 10h minus 1.86, okay, or actually, yep, let's just do that for right now, minus 3.72 h minus 1.86 h squared. Minus 8.14 divided by, okay, h. All right, and we want to know the limit as h approaches 0 of that. Okay. Now, what we need to do is we need to get the h's out of the denominator, and so when we're doing this, what we're going to find, what we really want to do is anything that doesn't have an h in it, we hope is going to eliminate itself. Okay. So if I rewrite this, this is going to be the limit as h approaches 0, okay, of 10 minus 1.86 is actually 8.14. So I have 8.14 minus 8.14, okay, and then this is going to then be, right, 10h minus 3.72h, okay, that's going to be 6.28h, so minus 6.28h, okay, or plus 6.28h, minus 1.86 h squared all over h. Okay, so this is then the limit as h approaches 0. These guys are going to cancel out. They go away. Okay, and what we're left with then is just this negative 1.86 h squared plus 6.28 h. Okay, and we're divided by h. And that's then just going to equal, right, the limit as h approaches 0 of negative 1.86h plus 6.28. And then we can just substitute in the 0. So now we can substitute in the 0, and we end up with, okay, 6.28, which is exactly what we ended up with before. So that was a good example of the two functions for the derivative are actually going to give you the exact same answers, because they will, right? It just depends upon, right, circumstances as to which one you want to use, right? I will take either one. I will honestly take either one. I think that for the purposes of these velocity questions, this is the easier algebra. I know it doesn't look easier, but it was actually the easier algebra. The other part requires like some synthetic division. All right. Stuff like this, it takes it.
Could you summarize it again?
Yeah, totally. Absolutely. So here's what happened, right? Okay, so that's the equation for our velocity, okay? All right, that's our equation for velocity. In this case, A is our t's, right? Okay, so our f is going to be this function h, and it's going to be 10t minus 1.86 t squared. Our a was 1. A equals 1. Okay, that was in the problem, right? 1 second is going to be the a that we put in here, and that's a t, right? Just that's the value for the x value. So I found f of a, or we could just rewrite this as f of 1, all right? And that was 8.14. That's going to go right here in the f of a part, okay? Then I found f of a plus h, which is just a little bit of algebra. In fact, maybe it's a lot of algebra, okay? But what it gave me then was it gave me, okay, when I simplified it, it gave me this equation right here. And we could have simplified it even more if we wanted to, okay? So I took that equation and I put it, it's going to be, it goes in for f of a plus h. So it goes right here, okay? Subtracted from f of a, okay? And divided by h, and we're going to take that limit as h approaches 0. Then it's just a matter of doing some algebra, okay? Then it's just a matter of doing some algebra where what we do is we kind of like cancel out all the terms that don't have h's in them, okay? And then we factor out the h, right? So basically this h, this, and this, they all canceled. And that's why I ended up with negative 1.86h plus 6.28. Then, just like any other limit, I'm going to plug in the 0, okay, in for h, and that gives me 6.28. And that's the process. The process for finding a derivative, really. Does that help clarify things or help to create a summary or synopsis?
Professor, I have a question.
Yeah, what's up there?
So I see where you got the 8.14 when you plugged in for the f of a.
Mm-hmm. Yeah.
So can you just explain the f of a plus h? So
okay,
where exactly are you doing that on the page? Where's the work for that one?
That's right here. That's this. Because a is 1, so it's f of 1 plus h.
Okay.
Right? So it's all of that work right there. Mm-hmm.
And where are you getting h from? Because isn't h as it approaches 0?
Okay. What the equation for the derivative, okay, takes the limit as h approaches 0. Okay. And so here's the thing. I talked about this inside of the video. It's the idea is that the intervals, if you remember with the velocity, okay, when we were looking at velocity, we looked at when the intervals for time got smaller and smaller and smaller. That's what h is. H in the velocity equation that's the intervals for time. So the intervals for time are getting smaller, all right? And then we want to know what's happening to the values for the position. What's happening with the values of position as the intervals get smaller? So as they get smaller, okay, what occurs? And that ends up being your derivative.
Okay.
And so that's where the h comes from.
All right. I'm a little still confused on that, but okay, I'll work on it. I'll probably see the video that you're talking about.
Yeah, hopefully that'll help. It's Yeah, it's just you want to think back to the time in which we were working with velocity, right? So the h's, right, are just those time intervals. I don't know if I can't see myself. The h's the time intervals, right? And so as those time intervals get smaller and smaller, h goes to 0, right? Because the interval goes to 0. We're looking at an instant, okay? And so all this is, right, is f of a plus h and f of a are the two endpoints, right, of where you're traveling, right? So you start at f of a plus h, or you start at really f of a, right? And you get to f of a plus h, all right? You subtract those two, that's how far you traveled, and h is how long it took you.
Okay.
Okay?
Mm-hmm. Yeah, I probably just have to review it and just go through the steps a little bit slower, but
Okay.
I think I'll figure it out.
All right. Let me know if you need anything.
Will do.
All right. Okay. That's tricky, folks. Tricky thought, actually. Okay. So then, now we get what's called the derivative. This is the derivative, and it's an instantaneous rate of change. And take a look. It's got the same equation, right? The difference is we call it f prime. Okay. And this is this thing here that's called f prime. So f prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a over h. Okay, and that's why, again, why it's so crucial to understand that functional notation, to be able to do composition. Okay, because what f of a plus h is, it's its composition. It's a composition of functions. Okay, and then we have the alternate. This is the one that actually is going to show up in your test next week. Okay, is f of x minus f of a over x minus a. Okay, there you're going to get the same answer. Whichever you choose, you will get the same answer. Okay? And so, if we look here, right, the slope of the tangent line, m tan, as we have it written here, is going to equal f prime of a. The slope of the tangent line at a, okay, is equal to the derivative at a. All right? Is equal to. They are the same. The two are the same. Okay? And so that gives me the equation of the tangent line, which we just did. There it is. There's the point slope form. Okay. So if the tangent line to y equals f of x at 4, 3 passes through the point 0, 2, find f of 4 and f prime of 4. Okay? So do those two things. Now, get this. Okay? Put this in the chat. What is f prime of 4 based upon what we just read? And saw and said. What is it? F prime of 4 is going to be what? Don't give me a number. I want to know what it means. What does f prime of 4 mean, given what we just did? Let's see if we can catch on with this. Anybody?
It's the derivative.
Yes, it's the derivative of f at 4. But what else is it? What's f prime of 4? With respect to this, you got the tangent line is y equals f of x at 4, 3, right? So we're asking a question about the tangent line, right? From the perspective of the tangent line, what is f prime of 4? All right. So this is a reading skill. Okay. The slope of the tangent line at A is equal to the derivative at A. So what is f prime of 4? Don't worry, it's okay if you're not right. Just tell me what you think. Right? Don't give me a number. I don't want a number. I don't want a value. I want to know just what it is as a concept. I don't know if it's hard to ask this question. Just throw it into the chat. People, they're probably answering. Ah, yes. Oh, yes. Thank God. Okay. All right. Yeah. Ready to change. Okay. Slope of the tangent line. I didn't realize you guys were all writing this. Thank you. You could. Fantastic. That's it. That's it. Oh, so smart. Okay. I am so glad. Stupid Zoom. You're all right, Misha. Everybody was corrected. Yeah, I'm sorry, Danny. Somebody's got to like unmute and say, hey, there's a bunch of things in the thing that's in there. Yeah, there's a bunch of things in the chat. People are answering because somehow it didn't show up. Okay. Yes, absolutely. F prime of 4 is the slope of the tangent line at 4. See, it did it again. No. Me too. I'm so glad. Huh. All right. So slope of the tangent line at 4. So what does that mean? So what's the numerical value for f prime of 4? What's the numerical value for f prime of 4? Find the slope of the tangent line. Right? F prime of 4 is going to equal, okay, 4 or 3 minus 2, 3 minus 2, yes, over 4 minus 0, which equals 1/4. Right? Because this point's on the tangent line, this other point's also on the tangent line. So the slope of the tangent line, use the slope formula. That one, nothing tricky. Well, it's just tricky stated, right? It's just, that's a slope, right? Okay. What is f of 4? Yep. Yep. Okay. You guys got to get that. That's the relationship between the point, right? Okay. And like how we write the point and what it means in functional terms. Okay. It's 3. F of 4 is 3. Okay. Plug in x equals 4, you get out 3. Because the tangent line touches f at 4, 3. So 4, 3 is also on f. Okay, 4, 3 is also on f. And so consequently, because the tangent line touches f at 4, 3, okay, we know that f of 4 equals 3. Okay, there we are. Ooh. Okay. Okay, so I'm going to move on from this one, okay? Let me know if I can't. We got a little bit of something like this for your homework. Let's first do E5 and then we'll go back on to E4, okay? So we'll look at E5. Find f prime of a. So f of x equals 3x squared minus 4x plus 1, okay? So what we need to know is you need to know that f prime of a is going to equal, and let's do it this way, f of a plus h minus f of a, or excuse me, the limit as h approaches 0 of f of a plus h minus f of a all over h. So go ahead and use that, okay? We have x, okay? Right? And, but a is going to stay a variable. Let's see if we can do this one. All right, I'll be right back. Okay, so just to start out with something, f of a plus h is going to equal, right, 3 times a plus h squared minus 4 times a plus h plus 1. Okay, so just to, you know, in case you had any wonderings, that's what's going to happen. When you are finished, put done in the chat, by the way. Or if you have questions, put your questions in the chat. Here we are. Yes, you are done. You are done, Blaine. All right. Got it. Thanks, Danny. Anybody else? If you've found it, if you've actually got yourself an answer, whether or not it's right or not, it's okay. Okay. Just put it up in the chat. X. Make these X's if we wanted to. Right. I actually want to know f prime of a. They're A's. Anybody stuck anywhere? You can unmute if you need to. That's right. You should have an A. It's actually f prime of a. So Valet, it should be 6a minus 4. It's an A, right? It should have an A. Okay, cool. Should definitely have an A. There should be A's in there. No H's, A's though. Okay. There we are. Okay. So this thing here is going to end up being, right, 3 times a squared plus 2ah plus h squared minus 4a minus 4h plus 1. Okay, which we can rewrite as 3a squared plus 2 plus 6ah plus 3h squared minus 4a minus 4h plus 1. Okay, they all have different terms. Great. Let's check. Say h, 3h squared, good. Minus 4a, minus 4h, okay, great. So now I'm just going to plug that into my equation here, okay? So this is going to then be 3a squared plus 6ah plus 3h squared minus 4a minus 4h plus 1 minus 3a squared minus 4a plus 1, all divided by h, and we're going to find the limit as h approaches 0 of that whole thing. Okay? Now our goal, okay, is to get rid of anything that doesn't have an h. We want to subtract out or to eliminate all the non-h terms. Otherwise, this limit doesn't exist. But, well, let's take a look, right? There's the 3a squared, and there's a minus 3a squared. Awesome. Here's a minus 4a and the minus 4a. That they also cancel, okay? And then the 1, that becomes a negative 1, right? And then the plus 1, so they cancel too. Yay, they're all gone. So this whole thing is going to then be the limit as h approaches 0 of 6ah plus 3h squared minus 4h divided by h. So this is now the limit as h approaches 0 of 6a plus 3h minus 4, which just simply equals 6a minus 4. And that is your f prime of a, your derivative. Okay? Okay. Yeah. This is tricky stuff. This is the difference quotient stuff that you maybe did in pre-calculus, right? You actually did a difference quotient. Now all we've done is we've added in the limit as h approaches 0. So the difference quotient is the same process. We're just now going to take the limit as h approaches 0. Okay, and then that's going to actually give us the value for our derivative. All right. Okay. Okay. So let me give you, so Misha asked me to do one of the precise definition questions from 2.4 before we finished up for today. Okay. So why don't we do that? And then I'll, kind of clarify a couple things, make sure that everything's clear for the exam. If you have any questions about the exam, please make sure that you email me, all right? Email me, I will get back to you. All right, so I'm gonna go in here, we're gonna go back to 2.4. We'll just do one of these precise definition questions. Okay. Just gonna go down here to the bottom. This will be inside of OneNote, or actually, you know what, why don't I just do it in the homework help solutions. So it's gonna be the homework help for chapter 2, okay? Let's say, for example, I want to prove, okay, I want to prove the limit as x approaches 3 of 4x minus 3 equals, right, 9. That's what I want to prove, okay? And so, I'm going to do, what I want to do is I want to show that for all epsilon greater than 0, there exists delta greater than 0 such that absolute value of x minus 3 less than delta implies, okay, that the absolute value of 4x minus 3 minus 9 is less than epsilon, okay? So what I want to do now is, in order to prove that, in order to do that proof, I'm going to start out here at the 4x minus 3 minus 9 is less than epsilon, and I'm going to get to x minus 3 is less than delta, okay? So here's my scratch work, like we've seen before, okay? So this is now, I've got to have the absolute value of 4x, and this 4x minus 12, right, is less than epsilon. So this now is, if I, like I'm doing my scratch, 4 times x minus 3, okay, is less than epsilon. Since 4 is positive, I can pull it out. 4 times x minus 3 less than epsilon, okay? And what I notice now is I'm very close to getting the x minus 3 less than delta. Okay, so then this is going to give me then x minus 3 is less than epsilon over 4. So what I'll do then is I'm going to set delta, let delta equal epsilon over 4. So that's the entirety of my scratch work. I mean, basically, I want to transform, right, this thing here, the epsilon one, you transform that into the delta one, okay? And whatever you end up with, okay, for the right-hand side of the equation, that's going to be your delta. You let delta equal that. So now, here's how you formally write it. We're going to say let delta equal epsilon over 4. If, okay, x minus 3 is less than delta, then x minus 3 is less than epsilon over 4. All right, by what I just defined, okay? So 4 times x minus 3 is less than epsilon. All right, just did some algebra there. Multiply both sides by 4, okay? Thus, you don't have to use the thuses, whatever. You can just write another sentence. Thus, right, 4x minus 12, right, which equals, and we'll just do this one. This is going to be 4x minus 3 minus 9, right? I want to get this. I want to write it that way. 4x minus 3 minus 9, okay, is less than epsilon. So now the proof is done. That's done, okay? So we just finish out by saying that the limit as x approaches 3 of 4x minus 3 is equal to 9. And that's the finishing of our proof.
So, Professor, basically, like on the left side, you're just you're solving for delta.
Yep.
And then you're plugging in delta into the other equation to turn it into the epsilon.
The epsilon equation. That's exactly right. So like somebody said, it's kind of like you went backwards, right? So like you did this in order to find delta, and then you go backwards in order to show that it's the epsilon.
Yeah, because I was doing the homework and I was doing like the scratch word part like pretty easily. But it was just the other side that I wasn't understanding how to do that.
Yeah, you know what?
I get it now.
Here's the deal. Just copy mine. I mean, like literally, you're just gonna change around the numbers, but like all the wording and things like that, and you're just gonna have slightly different algebra. That's it.
Okay. So
that makes sense.
You know how you left it at 4x minus 12? That would be wrong on the test, right? You want it to go all the way.
Yeah, you've got to get to this place right here because this is the actual. That's the actual proof part, right?
Okay.
This is the actual definition. Here's the definition. So you actually have to write this here, the 4x minus 3 minus 9, okay? Because that's the actual part of the definition, right?
Okay.
Without it, it's a missing part of the definition.
Okay.
Okay?
That makes sense.
Okay. All right. So we are done for today. Please, if you have, like I said, if you have any questions, email me. I'll check the discussion boards in case you've got questions about things. Notice in that announcement and also inside of OneNote, I've done probably about half of the homework. So I've actually put up solutions to about half of the homework up online inside of OneNote. Okay, so go in there, take a look at that. If you have questions, like I said, if they're math questions, throw them on the discussion board. I will check those, as well as probably your classmates. And then if there are questions about like protocols for the test, just email me. And then one thing to state is that I will not be answering email on Sunday. I'm taking Sunday off. Okay, so the last time I will answer email before Monday morning will be Saturday afternoon sometime. All right? So that's just to let you know. Okay. Have a great weekend. Study hard, everyone. Let's kill this. Let's do a great job on this test. I know you all can. I really believe that. Okay? I know you don't think so right now, but after a weekend of studying, you'll be there. You'll be there. I know. Okay.
Thank you, Professor. Have a good weekend.
You too, Valet. You're welcome. Yes. Yes, Carla. You can just continue. You're welcome. Thanks, guys. Are you posting the... I'll post the notes. I'll post the notes this afternoon. I'll do it like in just a couple of minutes. And Bill, I will take care of the OneNote for you guys too. For all the people who added late. I'll take care of that right now. Yes, the homework help is already inside of that announcement on Canvas, by the way, Carla. So it's all there. Anything that I got in the PDF, I will send over to you. It's called the answers to selected problems. So it's towards the bottom of the page. Okay. If you still can't, just email me and I'll email it to you directly. All right. Okay. And we're out. See you next week.